Welcome to Lesson 15 of the Mathematics module, Exponential Functions. This session runs approximately 120 minutes and is situated within the broader Math Tutor self-study track as Phase A of the curriculum. The central object of study is the exponential function f of x equals b to the x, where b is greater than 0 and b is not equal to 1. We will examine why this deceptively simple functional form, characterized by the placement of the variable in the exponent rather than the base, gives rise to behavior fundamentally distinct from polynomial functions. A particular emphasis will be placed on the natural base e, approximately 2.71828, whose defining property, that the derivative of e to the x is e to the x itself, renders it indispensable in both pure and applied mathematics. This self-replicating derivative is what makes calculus on exponential functions exceptionally elegant. The lesson concludes with 10 practice problems designed to reinforce the core competencies developed throughout the session. This lesson is generously sponsored by Subthesis. Interested learners may visit subthesis.com to explore additional self-study resources in mathematics, computer science, and machine learning. An exponential function is defined as f of x equals b to the x, where the independent variable appears in the exponent and the base b is a positive constant strictly not equal to 1. This structural distinction, variable in the exponent rather than the base, is what fundamentally separates exponential functions from polynomial functions, which take the form x to the k. This single functional form underlies a remarkably diverse range of phenomena: population growth in biology, radioactive decay in physics, compound interest in finance, and most continuous probability distributions encountered in machine learning. The agenda for today's lesson proceeds as follows. We begin with the behavior of exponential functions at a glance, covering growth versus decay patterns and their shared properties. Next, we address the technique of solving exponential equations by matching bases. We then introduce the natural base e and its defining calculus property, followed by compound interest as the prototypical real-world exponential. The machine learning connection, specifically sigmoid, softmax, and Gaussian functions, rounds out the conceptual material. Finally, 10 practice questions, a recap, and a preview of next week's content on logarithms. A critical distinction to establish early. Do not confuse exponential functions, where the variable is in the exponent, with power functions, where the variable is in the base. These families exhibit profoundly different growth rates. Let us examine the qualitative behavior of exponential functions. Consider the canonical growth function f of x equals 2 to the x. This function is strictly increasing for all real x, passes through the point 0, 1, and possesses a horizontal asymptote at y equals 0, which the curve approaches from above as x tends to negative infinity. Crucially, the curve never crosses or touches the x-axis. Exponential functions remain strictly positive throughout their domain. Now consider the decay counterpart, f of x equals 1/2 to the x. This function is strictly decreasing, yet it shares two fundamental properties with the growth case. It passes through the same point 0, 1, and it exhibits the same horizontal asymptote at y equals 0. Indeed, for any positive base b not equal to 1, f of 0 equals b to the 0, which equals 1. This is a direct consequence of the exponent 0 rule established in week 14. Any non-zero base raised to the 0th power equals 1. An elegant observation emerges from comparing these two curves. The growth and decay forms are reflections of one another across the y-axis. This symmetry reveals that growth and decay are not genuinely distinct families. They constitute the same family with reciprocal bases, since 1 over b to the x equals b to the negative x. Common errors to anticipate: writing b to the 0 equals 0 rather than b to the 0 equals 1, and sketching the exponential curve as though it intersects the x-axis, when in fact it remains strictly positive for all x. This slide highlights a crucial comparison between polynomial and exponential growth. While polynomial functions like x cubed grow quickly, exponential functions like 2 to the x eventually overtake them by enormous margins. Consider the values side by side. At x equals 5, x cubed gives 125, while 2 to the 5 gives just 32, so the polynomial is actually larger. At x equals 10, x cubed gives 1000, while 2 to the 10 gives 1024, and they are roughly equal. But at x equals 20, x cubed gives 8000, while 2 to the 20 gives over 1 million. And at x equals 30, x cubed reaches 27,000, while 2 to the 30 exceeds 1 billion. This dramatic divergence illustrates the key rule: exponential functions always eventually dominate polynomial functions, no matter how large the polynomial degree. The crossover may happen late, but once it occurs, the exponential pulls away at an accelerating pace. This principle underlies why exponential growth in population, computing power, and compound interest becomes so dramatic over long time horizons. Exponential functions can be shifted, reflected, and stretched, just like any other function family. Understanding these transformations allows you to graph a wide variety of exponential functions, starting from a single parent function. The parent function here is f of x equals 2 to the x. A vertical shift, such as f of x equals 2 to the x plus 3, moves the entire graph up by 3 units. This changes the horizontal asymptote from y equals 0 to y equals 3. A horizontal shift, such as f of x equals 2 to the quantity x minus 2, moves the graph 2 units to the right. The shape stays the same, but every point shifts horizontally. A reflection, written as f of x equals negative 2 to the x, flips the graph over the x-axis. Instead of approaching 0 from above, the reflected graph approaches 0 from below, and all output values become negative. A vertical stretch, such as f of x equals 3 times 2 to the x, makes the graph grow faster by multiplying every output by 3. The y-intercept moves from 1 to 3, but the horizontal asymptote remains at y equals 0. The general form combining all transformations is f of x equals a times b to the quantity x minus h plus k. Here, a controls vertical stretch and reflection, h controls horizontal shift, and k controls vertical shift. We now turn to a fundamental technique for solving exponential equations: base matching. The underlying principle is straightforward and rests on the one-to-one property of exponential functions. If b to the m equals b to the n for some base b greater than 0 with b not equal to 1, then necessarily m equals n. Consequently, when both sides of an equation can be expressed with a common base, we may equate the exponents directly. Example 1. Solve 2 to the x equals 32. We recognize that 32 equals 2 to the fifth. Therefore, 2 to the x equals 2 to the fifth, and by the one-to-one property of the exponential function, x equals 5. Example 2. Solve 3 to the quantity x plus 1 equals 27. We observe that 27 equals 3 cubed. Thus, 3 to the quantity x plus 1 equals 3 cubed, which yields the linear equation x plus 1 equals 3, giving x equals 2. It is important to note the logical structure here. Matching bases is the precondition. equating exponents is the conclusion. A common error is to reverse this, attempting to set bases equal rather than exponents. A natural question arises. What if the equation cannot be readily reduced to a common base? Consider, for instance, 2 to the x equals 5. Since 5 is not an integer power of 2, the base matching technique does not apply directly. For such equations, one requires logarithms, the subject of next week's lesson. Another frequent mistake involves failing to fully convert one side of the equation. One must rewrite 32 as 2 to the 5th before the comparison is meaningful. Leaving 32 in its decimal form renders the technique inapplicable. Why does the mathematical community privilege e over seemingly more intuitive bases such as 10 or 2? The answer lies in a remarkable calculus property. E to the x is its own derivative. That is, the derivative of e to the x with respect to x equals e to the x. No other exponential base possesses this self-replicating property, and it is precisely this characteristic that renders calculus involving exponential functions dramatically simpler when e serves as the base. The numerical value of e is approximately 2.71828. It is an irrational number, meaning it cannot be expressed as a ratio of integers. Moreover, it is transcendental, meaning it is not the root of any polynomial equation with rational coefficients. In this respect, e shares a structural kinship with pi. Both are constants of nature that emerge inevitably wherever smooth multiplicative or periodic processes occur. The significance of e extends well beyond pure mathematics. Nearly every continuous probability distribution and machine learning activation function employs e as its base. This is not a matter of convention, but of mathematical necessity. The self-derivative property ensures that gradient computations, the engine of optimization algorithms, remain analytically tractable. Two common errors merit attention. First, students sometimes treat e as a variable rather than a fixed constant. It is no more variable than pi. Second, there is occasional confusion between e as the base of the natural exponential and its role in defining the natural logarithm. While the two concepts are intimately linked, since the natural logarithm is the inverse of e to the x, the exponential comes first conceptually. E is defined as the unique base whose exponential function is its own derivative. Compound interest provides perhaps the most intuitive and historically significant illustration of exponential growth. The discrete compounding formula is A equals P times the quantity 1 plus R over N raised to the power N times T. Here, P denotes the initial principal, R the annual interest rate expressed as a decimal, N the number of compounding periods per year, and T the elapsed time in years. Observe that the independent variable t appears in the exponent, confirming that compound interest is indeed an exponential process. Each compounding period multiplies the accumulated balance by the factor 1 plus r over n, and the repeated application of this multiplicative step over n times t periods yields the exponential structure. A profound result emerges when we consider the limiting case. As n approaches infinity, that is, as compounding becomes continuous, the discrete formula converges to A equals P times e to the RT. This is one of the canonical derivations in which Euler's number e arises naturally, not by definitional decree, but as a structural consequence of the limiting process. The expression 1 plus 1 over n raised to the nth power approaches e as n grows without bound. This limit generalizes to the continuous compounding formula. The broader implication is this. Whenever one encounters continuous growth or decay at a fixed proportional rate, whether in finance, population dynamics, radioactive decay, or signal attenuation, one is observing the same mathematical structure as compound interest at the continuous limit. Two errors are common in this context. First, substituting n equals 0 into the discrete formula is undefined, as the formula presupposes at least one compounding period per year. Second, students sometimes confuse the annual rate r with the per period rate. When n is greater than 1, the rate applied per period is r divided by n, not r itself. This slide presents a worked example of compound interest with real numbers. We are investing $1,000 at an annual interest rate of 5% for 10 years and comparing two compounding methods. With monthly compounding, we use the discrete formula. The base is 1 plus 0.05 divided by 12, and we raise it to the power of 12 times 10, which is 120. Multiplying by the principal of $1,000 gives us approximately $1,647.01. With continuous compounding, we use the formula A equals P times e to the RT. That gives us 1,000 times e to the power of 0.05 times 10, which equals 1,000 times e to the 0.5. This works out to approximately $1,648.72. The key takeaway is that the difference between monthly and continuous compounding is remarkably small, just $1.71 over a full decade. This illustrates why continuous compounding is such a useful approximation. It simplifies the mathematics considerably while producing results that are nearly identical to frequent discrete compounding. Three of the most widely used formulas in machine learning are built directly upon the exponential function e to the x. Understanding why requires appreciating the structural properties that e to the x provides: strict positivity, smoothness through infinite differentiability, rapid growth, and, most critically, the self-derivative property. First, the sigmoid function. Sigma of x equals 1 divided by the quantity 1 plus e to the negative x. This function maps any real-valued input to the open interval from 0 to 1, making it ideal for producing probability estimates. It serves as the activation function in logistic regression, and was historically the default nonlinearity in neural network hidden layers. The negative exponent ensures that large positive inputs yield outputs near 1, while large negative inputs yield outputs near 0. Second, softmax. The softmax of x sub I equals e to the x sub I, divided by the sum of e to the x sub j across all j. Softmax generalizes sigmoid to the multiclass setting. By exponentiating each logit, all values become strictly positive. Dividing by their sum normalizes the output to a valid probability distribution. This operation transforms a vector of arbitrary real numbers into a vector of non-negative values that sum to 1. Third, the Gaussian or normal distribution. F of x equals 1 divided by sigma times the square root of 2 pi, multiplied by e to the power of negative x minus mu squared, divided by 2 sigma squared. The exponential of a negative quadratic in the exponent produces the characteristic bell curve. The Gaussian appears throughout statistical learning, from anomaly detection to Gaussian processes to Bayesian inference. The common thread unifying all three is this: e to the x is positive, ensuring probabilities and densities remain non-negative. It is smooth, ensuring gradients exist everywhere. And it is self-derivative, ensuring that gradient descent through these functions remains analytically clean. Common errors include misreading sigmoid as 1 divided by 1 plus e to the x. Note the critical negative sign in the exponent. Another error is omitting the normalization denominator in softmax, which must sum across all classes to produce a valid distribution. This slide explores exponential decay through one of its most famous real-world applications, radioactive half-life. In particular, we examine carbon-14, whose half-life is approximately 5,730 years. Consider a sample that starts with 100 grams of carbon-14. After one half-life of 5,730 years, half the material has decayed, leaving 50 grams. After two half-lives, or 11,460 years, we are down to 25 grams. After three half-lives, 17,190 years, only 12.5 grams remain. Each interval reduces the remaining quantity by exactly half, which is the signature of exponential decay. This same mathematical structure appears in many other contexts. Drug metabolism follows exponential decay as the body eliminates medication from the bloodstream. Newton's law of cooling describes how a hot object's temperature decreases exponentially toward the ambient temperature. Asset depreciation in accounting often uses exponential models, and signal attenuation in electronics follows exponential decay as signals weaken over distance. The key insight is that all of these processes share the same underlying mathematics. The quantity decreases by a fixed proportion over each equal time interval, producing the characteristic exponential decay curve that approaches zero but never quite reaches it. We now transition to the practice component of this lesson. The following 10 questions are designed to assess comprehension of the core concepts presented thus far: exponential function evaluation, recognition of growth and decay patterns, the base matching technique for solving equations, properties of the natural base e, compound interest, and the role of exponentials in machine learning. For each question, pause to formulate your answer before proceeding to the solution. Active recall, the practice of attempting retrieval before seeing the answer, is among the most effective strategies for long-term retention, as established by the cognitive science literature on spaced repetition and testing effects. Question 1. Given f of x equals 2 to the x, evaluate f of 3. The answer choices are A. 6, B. 8, C. 9, D. 5. Pause now to select your answer. The correct answer is B. F of 3 equals 2 to the third, which equals 2 times 2 times 2, which equals 8. This is a direct application of the definition of exponentiation as repeated multiplication. The distractor a equals 6 is designed to catch the common error of computing 2 times 3 equals 6, that is, confusing exponentiation with multiplication. This confusion between 2 multiplied by 3 and 2 raised to the third power is one of the most persistent arithmetic errors among students new to exponential functions. The operation b to the x denotes repeated multiplication of b by itself x times, not the product b times x. Question 2. Given f of x equals 1/2 to the x, evaluate f of 0. The answer choices are A. 0, B. 1, C. 1/2, D. Undefined. Pause now to select your answer. The correct answer is B. F of 0 equals 1/2 to the 0, which equals 1. This follows directly from the zero exponent rule, which states that any non-zero base raised to the 0th power equals 1. The rule holds universally. B to the 0 equals 1 for all b not equal to 0. The distractor a equals 0 targets a pervasive misconception, the erroneous belief that anything to the 0 power is 0, confusing b to the 0 with 0 times b. This is perhaps the single most common error associated with exponential functions at the introductory level. The distractor c equals 1/2 targets the error of computing f of 1 instead of f of 0, substituting the base value rather than applying the 0 exponent. Distractor D is included for students who may believe the expression is somehow undefined, which it is not. Question 3. Which of the following describes the graph of y equals 2 to the x? The answer choices are A. Decreasing, B. Increasing with a horizontal asymptote at y equals 0 from above, C. Periodic, D. Symmetric about the y-axis. Pause now to select your answer. The correct answer is B. The function y equals 2 to the x is strictly increasing for all real x. As x tends to negative infinity, the function values approach 0 but never reach it, hence the horizontal asymptote at y equals 0 approached from above. As x tends to positive infinity, the function grows without bound. Let us examine why the other options are incorrect. Option A describes the decay function 1/2 to the x, not the growth function 2 to the x. Confusing these two is tantamount to confusing a base greater than 1 with a base between 0 and 1. Option C, periodicity, is a characteristic of trigonometric functions such as sine and cosine. Exponential functions are emphatically not periodic. Option D, symmetry about the y-axis, would require f of x to equal f of negative x for all x, the defining property of even functions. Since 2 to the x does not equal 2 to the negative x in general, the exponential function is not even. Question 4. Free response. Solve the equation 2 to the x equals 32. Pause now to work through this problem. The answer is x equals 5. The solution proceeds by the base matching technique. Recognize that 32 can be expressed as a power of 2, namely 32 equals 2 to the 5th. Substituting, we obtain 2 to the x equals 2 to the 5th. Since the exponential function with base 2 is 1 to 1, equality of the outputs implies equality of the inputs, yielding x equals 5. This question reinforces the base matching method introduced earlier in the lesson. Note that while logarithms could also solve this equation by taking log base 2 of both sides, the base matching approach is more direct and computationally simpler when the right-hand side is a recognizable power of the base. Developing fluency with small powers of common bases, such as powers of 2, 3, 5, and 10, is an essential arithmetic skill for this technique. Question 5. Free response. Solve the equation 3 to the quantity x plus 1 equals 27. Pause now to work through this problem. The answer is x equals 2. We begin by expressing 27 as a power of 3. 27 equals 3 cubed. The equation becomes 3 to the quantity x plus 1 equals 3 cubed. Invoking the one-to-one property of the base 3 exponential function, we equate the exponents. X plus 1 equals 3. Solving this linear equation yields x equals 2. This problem introduces a modest but important complication relative to question 4. The exponent is not simply x, but a linear expression x plus 1. After matching bases and equating exponents, one must still solve the resulting algebraic equation. This two-step process, first reduce to a common base, then solve the exponent equation, is the general pattern for base matching problems. A common error is to perform arithmetic on the original numbers rather than operating in exponent space. For instance, computing 27 minus 1 equals 26 and treating that as the answer confuses the base level arithmetic with the exponent level algebra. The rewrite must occur in the exponents, not in the base values. Question 6. What is the approximate numerical value of e? The answer choices are A. 3.14, B. 2.72, C. 1.62, D. 1.41. Pause now to select your answer. The correct answer is B. E is approximately 2.72, or more precisely 2.71828, and so on. It is the unique real number such that the exponential function e to the x equals its own derivative. Each distractor corresponds to a well-known mathematical constant, testing whether students can distinguish among them. Option A, 3.14, is the familiar approximation of pi, the ratio of a circle's circumference to its diameter. Option C, 1.62, approximates the golden ratio phi, which equals 1 plus the square root of 5, all divided by 2. It arises in number theory, combinatorics, and phyllotaxis. Option D, 1.41, approximates the square root of 2, the length of the diagonal of a unit square, and the first number proven to be irrational by the ancient Greeks. Memorizing e to at least 2 decimal places, 2.72, is a practical necessity for estimation and sanity-checking computations involving exponential growth, compound interest, and probability distributions. Question 7. Identify the sigmoid function used in logistic regression. The answer choices are A. 1 divided by 1 plus e to the negative x, B. e to the x, C. log x, D. x squared. Pause now to select your answer. The correct answer is A. Sigma of x equals 1 divided by the quantity 1 plus e to the negative x. The sigmoid function is the canonical activation function for binary classification in logistic regression and was historically the default nonlinearity in neural network architectures. The sigmoid maps any real-valued input to the open interval from 0 to 1, producing an output interpretable as a probability. This bounded, monotonically increasing S-shaped curve has several desirable properties. It is infinitely differentiable. Its derivative can be expressed elegantly as sigma of x times the quantity 1 minus sigma of x, and its output naturally represents the posterior probability of class membership. Option B, e to the x, is the raw exponential function. It is unbounded above and therefore cannot directly represent a probability, which must lie between 0 and 1. Option C, log x, is the natural logarithm, which is the inverse of the exponential, but maps only positive reals and is unbounded below. Option D, x squared, is a polynomial or quadratic function with no relationship to probabilistic classification. Question 8. The compound interest formula employs which type of function? The answer choices are A. Linear functions, B. Quadratic, C. Exponential, D. Trigonometric. Pause now to select your answer. The correct answer is C. Exponential. The compound interest formula A equals P times the quantity 1 plus R over N raised to the power N times T places the time variable T in the exponent. This is the defining characteristic of exponential functions. Each compounding period multiplies the accumulated balance by a fixed factor, and this iterated multiplication over time produces exponential growth. The distinction between linear and exponential growth is precisely what separates simple interest from compound interest. Under simple interest, the accrued amount grows linearly, with each period adding the same fixed dollar amount. Under compound interest, each period multiplies by the same factor, producing accelerating growth. This multiplicative versus additive distinction is the fundamental qualitative difference between exponential and linear functions, and it is why compound interest ultimately dominates simple interest over long time horizons. Question 9. Free response. Simplify the expression e to the x multiplied by e to the 2x. Pause now to work through this problem. The answer is e to the 3x. This follows from the product rule of exponents, which states that when multiplying expressions with the same base, one adds the exponents. b to the m times b to the n equals b to the quantity m plus n. Applying this rule with base e, we obtain e to the x times e to the 2x equals e to the quantity x plus 2x, which equals e to the 3x. This is a direct application of the exponent laws established in week 14, now applied with the natural base e. The product rule is one of the most frequently invoked identities in exponential algebra, and fluency with it is essential for simplifying expressions that arise in calculus, differential equations, and machine learning gradient computations. A common error is to multiply the exponents rather than add them, computing e to the 2x squared instead of e to the 3x. This confusion arises from conflating the product rule with the power rule. The product rule says, same base, multiply expressions, add exponents. The power rule says, base raised to a power, then raised again, multiply exponents. The product rule applies when two exponential expressions with the same base are multiplied. The power rule applies when a single exponential expression is raised to an additional power. Question 10. Open reflection. Why is e to the x considered special in the context of machine learning? Take a moment to consider your response before moving on. This is an open-ended reflection question rather than a fixed answer problem. The central insight is that e to the x is its own derivative. The derivative of e to the x with respect to x equals e to the x. This self-replicating property under differentiation is unique among exponential functions and has profound consequences for optimization. In machine learning, model training proceeds via gradient descent, which requires computing derivatives of the loss function with respect to model parameters. Functions built from e to the x, such as sigmoid, softmax, and the Gaussian density, inherit analytically clean gradient expressions precisely because the derivative of e to the x does not introduce new functional forms. The derivative of sigmoid, for instance, simplifies to sigma of x times the quantity 1 minus sigma of x, an expression entirely in terms of the function's own output. Beyond differentiability, E governs several foundational processes: continuous compounding as the limit of discrete compound interest, radioactive half-lives through exponential decay, and the natural logarithm link function in generalized linear models. Cross-entropy loss, the standard objective for classification tasks, is derived directly from the logarithm of softmax outputs, which in turn are exponentials. In summary, the ubiquity of e to the x in machine learning is not a historical accident, but a mathematical inevitability. Differentiability combined with self-derivative behavior makes e to the x the optimal base for any framework that relies on gradient-based optimization. Let us recapitulate the essential content of Week 15. The overarching theme may be distilled to a single sentence. An exponential function places the variable in the exponent, and the natural exponential e to the x is distinguished by being its own derivative. Over the course of this lesson, you have accomplished the following learning objectives. You computed exponential function values for specific inputs. You recognized the qualitative distinction between growth, where b is greater than 1, and decay, where b is between 0 and 1. You identified their shared properties, passage through 0, 1, and a horizontal asymptote at y equals 0. You solved basic exponential equations using the base matching technique, and you connected exponential functions to three pivotal machine learning constructs: the sigmoid activation in logistic regression, softmax for multi-class classification, and the Gaussian distribution. Three families of common errors were addressed throughout. First, the b to the 0 confusion, the erroneous assertion that b to the 0 equals 0 rather than the correct answer of 1. Second, the e as variable trap, treating Euler's number as an algebraic unknown rather than a fixed constant. Third, the polynomial versus exponential confusion, failing to recognize that x squared and 2 to the x belong to fundamentally different function families with dramatically different growth rates. Each of these outcomes connects forward to subsequent material. The base matching technique generalizes to taking logarithms of both sides, the subject of week 16. The self-derivative property of e to the x becomes the engine of backpropagation through sigmoid and softmax layers in neural networks, and the asymptotic behavior of exponential functions governs the phenomenon of vanishing gradients in deep networks, a critical consideration in modern deep learning architecture design. Looking ahead to the final week of this module, week 16 addresses logarithms, the inverse operation to exponentiation. Just as subtraction undoes addition and division undoes multiplication, the logarithm undoes the exponential. The lesson will cover the three fundamental logarithmic identities: the product rule, log of a times b equals log a plus log b; the quotient rule, log of a divided by b equals log a minus log b; and the power rule, log of a to the n equals n times log a. Students will practice converting between logarithmic and exponential forms, solidifying the conceptual duality between these two representations. The machine learning connection deepens considerably with logarithms. Every machine learning algorithm that maximizes likelihood in practice maximizes log likelihood instead, a transformation that converts products of small probabilities into sums, preventing numerical underflow on finite precision hardware. Cross-entropy loss, the standard objective function for classification tasks, is fundamentally a single logarithmic identity applied to softmax outputs. Understanding logarithms is therefore not merely an algebraic convenience, but a computational necessity in modern machine learning. This concludes Lesson 15, Exponential Functions. Thank you for your engagement with this material. If you found this lesson valuable, please consider liking and subscribing. It assists the algorithm in surfacing this content for additional learners who may benefit from it. This lesson has been sponsored by Subthesis. Visit subthesis.com for self-study resources in mathematics, computer science, and machine learning. We look forward to continuing with you in week 16, where logarithms will complete the exponential logarithmic duality that underpins so much of applied mathematics and machine learning.